Ask any engineer how to check membership against a billion keys, and the answer is almost always hash set. That means paying a billion keys worth of memory just for yes or no answers. A Bloom filter gets the same answer for a fraction of that cost, trading a small tunable error for never storing a key. A CDN serving a few billion cache keys, or a web crawler tracking every URL it has already fetched, faces the same question constantly. Have I seen this exact key before? Yes or no. Answer wrong by claiming you have not seen something when you actually have, and at best you waste work, at worst you break correctness. The cache treats a stored object as missing and fetches from origin again. The crawler recrawls a page it already indexed, and duplicates become real bugs. So you want that direction of error off the table entirely, but answer wrong in the other direction, occasionally claiming you have seen something when you have not. And the cost is small. You just do the expensive disk read or the network call you were trying to avoid, and you get the correct answer anyway. That asymmetry matters, because storing every actual key in a hash set or a database index to get a perfect answer means paying for memory that scales with the size of your entire dataset. If the guard in front of your storage is as expensive as the storage itself, it is not guarding anything. What you need is a check that is smaller and faster than the system it protects, and that never lies about a negative. The simplest fix is the one every intermediate developer reaches for first. Take every key, run it through a hash function, and drop it into a bucket array. That is a hash set. Lookup means hashing the key again, jumping straight to its bucket, and checking what is actually stored there. Average case? That is O of 1, constant time. Whether you have 1,000 keys or a billion, as long as the hash function spreads keys well, and the table resizes to keep its load factor low. In the worst case, with pathological or adversarial collisions, a lookup can degrade toward linear time, and the answer it gives back is exact. No false positives, no false negatives ever, because after the hash points you at the right bucket, you compare the actual stored key itself before confirming a match. If your dataset fits in memory, and memory is not the thing you are rationing, this is correct, it is fast, and there is no reason to reach for anything cleverer. The problem only shows up once you ask what a hash set actually costs to store billions of full keys. That O of 1 lookup is not the whole story. O of 1 describes the time, not the space. A hash set still has to keep the key itself for every single entry, not just a short hash of it, or two keys that collide become impossible to tell apart. And that key has to live somewhere in memory. So the total footprint grows linearly, with n. 10 million keys is fine on a laptop. A billion is a different problem. Call it 20 bytes per entry all in, and that is a conservative floor, since real implementations often run several times higher once you count object headers and load factor slack. A billion entries is at least 20 gigabytes, just for the membership check, before a single byte of the content you are guarding. 20 gigabytes still fits on a big server, but it competes with the actual data you serve, and at 10 billion keys, or with richer keys, the check alone outgrows the machine. It spills to disk, or it gets sharded across a network of servers, and every lookup risks a page fault or a round trip. If checking the checker costs as much as the thing it protects, the entire premise collapses. You are back to paying full price, just one layer removed. Something has to give, and it will not be correctness on the negative side. It has to be exactness itself. So drop the key itself entirely. Do not keep anything that lets you reconstruct which keys you have seen. Instead, allocate a single bit array of m bits, all 0 to start, and let that array be the entire structure, forever, no matter how many keys pass through it. 10 keys or 10 billion keys, the array stays m bits. That fixed size is the whole point. You are not trading away correctness for no reason. You are trading it specifically to break the link between memory and n. Here is how you use those m bits. To insert a key, run it through k different hash functions, not one. Each hash function takes the key and produces a position somewhere in that array, from 0 up to m-1. You get k positions back and you set each of them to 1. That is the entire insert operation. No key is written anywhere. All that changed is that k bits flipped from 0 to 1. Lookup runs the identical k hash functions on the key you are asking about. Same key, same math, so you get the exact same k positions back that you would have gotten at insert time. Now you check those positions in the array. And here is where the two guarantees split apart. If even one of those k bits is still 0, you know for certain that this key was never inserted. Because if it had been inserted, that insert would have set every one of those k bits to 1. And bits in this structure only ever go from 0 to 1, never back. A 0 at any of the k positions is proof of absence. That is a hard guarantee, not a probability, and it is exactly the guarantee the problem demanded, 0 false negatives. But if all k bits come back as 1, you cannot conclude the key was inserted. You can only say maybe, because those bits are shared. Every key you insert is scattering its k1s across the same m-bit array as every other key. A completely different key, one you never inserted, might happen to hash to k positions that were already set to 1 by other keys entirely. Check its bits, find all 1s, and you get a false positive, even though that specific key never went in. That collision is the one and only source of error in the whole structure, a direct consequence of sharing bit positions across keys. So the mechanism gives you exactly 2 outcomes. Definitely not present, which is always correct, and probably present, which is correct most of the time and wrong in a way you can quantify. What decides how often that maybe is actually a lie comes down to just 3 numbers: how big you make m, how many hash functions k you run, and how many keys you have actually inserted. That false positive rate is not a mystery, it is a formula. The probability of a false positive works out to approximately 1 minus e to the power of negative kn over m, all raised to the k. That looks dense, but the intuition is simple. It is governed entirely by the ratio of bits to elements, m over n, and by how many hash functions k you run. More bits per element, lower false positive rate. More hash functions, up to a point, also lower. Past that point, more hash functions actually hurts because you are setting more bits to 1 on every insert, filling up the array faster. There is a sweet spot, and it has a clean closed form. The optimal k is approximately m over n times the natural log of 2. Plug that back in, and for a given memory budget, that choice of k minimizes your false positive rate. If that rate still is not low enough, there is exactly one lever left to pull: allocate more bits. Shrinking that rate is not free. It is a direct trade, memory for accuracy, and the formula tells you exactly how much of one you get for the other. But there is a guarantee this structure cannot give you at any m or k, and that is deletion. You cannot remove a key by clearing its bits, because those bits are shared. Another key you never intended to touch may depend on that exact same bit staying set to 1. Clear it, and you have just introduced a false negative, silently, the one error this structure was built to make impossible. If you genuinely need deletion, there is a variant, a counting bloom filter, which replaces each bit with a small counter, incrementing on insert and decrementing on delete. It works, but every position becomes a small counter, typically 4 bits instead of 1, so it costs roughly 4 times the memory. So the accuracy dial and the deletion feature both cost you the same thing memory was supposed to save. This structure sits directly inside storage engines you have probably already used. RocksDB and LevelDB can attach a bloom filter to every SSTable on disk. Before doing an actual disk seek for a key, the engine checks that table's filter first. A 0 at any of the k-bit positions means the key is definitely not in that file, so the engine skips the seek entirely and moves on. Cassandra does the same thing per SSTable. For the same reason, disk reads are the expensive resource, and the filter is cheap enough to check thousands of times without noticing. The same shape fits any client that cannot hold the authoritative list itself. Rather than shipping a full block list of malicious URLs to every browser, ship a compact filter, so a URL that hashes to any 0-bit is safe with no network call, and only a maybe costs a round trip to the service that holds the real list. Notice the pattern repeats exactly. The filter never operates alone. It sits in front of an authoritative source, the real SSTable, the real block list, and its only job is to cheaply rule out the negatives, so that the expensive, exact check only runs on the fraction of cases where it might actually be needed.